I'm Parfait Archade. My background is telecommunication engineering and specialize in electronics. And I have also some kind of MBA, Master in Business Administration. And I started with entrepreneurship. And after that, I jumped to, I saw that there's a lot of project or problem that we can solve easily with classical computation. Okay, the classical computation is a computation that we know that is based on binary model, 1 0 1 0 1 0. Problems when we want to talk about combinatorial problems, optimization problems, these problems are very hard to solve, and this problem has a category that is NP hard. They call this problem NP hard. Also drug discovery, material synthetics, these problems are not exactly solved by classical computation. Okay, so how can we solve this problem? So by that way was when I was exploring, I saw that there's an emerging field called quantum computing that can help by solving these problems. Okay. So basically, I started there. I have a PhD in quantum computing, and my thesis were on hard constraints optimization problems. So I'm specialized in solving hard problems with constraints. So we can solve it. I can solve this problem by writing the optimization function of this problem or using quantum machine learning by solving this problem. Quantum machine learning means quantum plus machine learning. So I have the ability to combine this and give solution to all these optimization problems. So I'm working in the group with Luis and Maitani and a lot of people. And we are working on, and we will see here, we are working on synthetic data. How can we extract qualitative information from ABM? Because CDs are very complex systems to solve. And solving these systems, we cannot spend time, like 20 years, to see how CDs is moving or is evolving. We need some kind of a simulation, living lab, where we can put some kind of agent, artificial engine, and we can extract information to see how can we improve the CD. To do that, we will see here ABM, and we see that maybe it's limited. How can we add, let us say that, sentiments, behavior to this agent to extract very qualitative data or qualitative information that help citizens to build or to create the city of the future. This is part of the work that I'm working. And today, my talk will be some kind of quick introduction in artificial intelligence and part of the humanized ABM. Okay? There's a question, comment? So, introduction on ABM, intelligence artificial. First of all, we need to understand that the intelligence artificial was born in 1959, but the main idea was simulating human intelligence process by machine. This is the first idea, okay? And inside the intelligence artificial, we have a group that is machine learning, that we know that machine learning is enable machine to learn from that data and experience, okay? And we will see that without data, we don't have statistics, we don't have mathematics, and we don't have machine learning. And inside a subset of machine learning is called deep learning, where we use like a neuronal network to improve and to inspire by the brain structure to solve this problem that we are talking about. All these techniques are not exact solution. They are like a kind of approximation. Okay, when we are talking about machine learning, we are not thinking about exact solution. Okay, this is very important. And between this machine learning, intelligent artificial, now we have the generative AI that is still in the cradle, but is very suppressing now. Because the result that we are seeing from the generative AI are amazing. Even if what scientists are saying, we didn't reach yet 2% of the generative AI, but the results that we are seeing are very, very amazing. The base of generative AI, like LLM and so on, is only predict the next step of the information that we have. Only by doing this, we can do all this stuff that we are seeing about ChatGPT and Llama and so on. So the only thing that they are doing is predict the next word, the probability of the next step. Now they are putting reasoning, they are putting a lot of stuff to see how can we work on that. Only by predicting the next step, we saw the new information from OpenAI, and the outcome is very, very important and very, very impressive. So this is a very important field. Here is type of machine learning that can pray and think by itself, but we are still in the cradle. Here I prepare some very quick application that we can see about AI and so forecasting to analyze historical data and identify pattern. Sentiment analyzing, that where we can use natural language or also LLM to solve these problems. And we can see also process of optimization, resource allocation, copilot, agent, chatbot, decision optimization. This is some kind of application that we can see in AI. But we cannot talk about AI without seeing which kind of challenge this application has. Bias, because we are training. When we train, we have bias. Environment. This is also important. Talking about environment, the part that I want to focus on is about the energy that we need to train AI. This is very important. Training AI is not efficient in the point of view of energy. And somehow people from Google say that they had, before OpenAI, the architecture to train all the algorithm, but they didn't do it. Why? Because they saw that they will need a lot of energy, a lot of power, and they decide to do not do it. So classical computation and machine learning use a lot of power, a lot of energy. And this is something that we have to take in consideration. It's not the topic, but one of the things that quantum computing comes here to solve is about this energy efficiency. That is important for city science. Copyright, ethics stuff, AI have a lot of ethics stuff, and the thing that we will see, or the workshop on what we will work, we will focus on ethics stuff also. Cybersecurity, regulation. There's a lot of things about regulation, and hallucination. Hallucination is about the context. So all these challenges are in when we want to work with AI, or where we want to work with deep learning, generative AI, and so on. Question? This is important for people that are starting or are doing machine learning and AI stuff. There's no paradise without data. We cannot talk about statistics, about machine learning without having data. Because we saw that machine learning learn from experience, learn from data. And when we say data, we want to say also qualitative data. This is important. So without data, there's no machine learning. Okay? This is important. Because by building the model that we want to build, we started with database, set of data. We have the input data. We need also the output data. And the black box between the input data and the output data is some kind of function that find the relation between the input data and the output data. And this function could be linear. And so in this case, we will say that we are doing linear, like a linear interpolation or something like that. If it's not linear, it will be another function. But the main idea that we are following is to find the relationship between the input and the output. And this is important. So we have data. Without data, this black box cannot do anything. And if the data that we have is not very high quality, it's lost. Okay, it's very important. So, and in machine learning, as we have seen, there's 3 feet. Okay, we know a lot about this part because everyone is doing machine learning about supervised learning. Supervised learning, that means we are supervising what we are doing. So we have some kind of label or some kind of class, and we want to see if what we are training, what we are doing, relate with the label that we have. This is the kind of. And that we have like classification and regression. Classification is when we have clear that we want to make decision that the input that is coming is going to the one class or to another class. Like customer rotation, medical diagnostic, you have cancer or no cancer. So this classification stuff. Facial recognition. What I'm seeing, is it a chair? Is it a dog? Is it the cat? This is classification. And in the case of regression is that I have few information about data. I have few data, I don't have all the data. But in the future, maybe I want to make some kind of prediction on how this is working on. So the main idea is finding some kind of cube or some kind of function that can give me information about some data or some input information that I didn't have in my data set. So it's some kind of, this is very interesting when we are trying to find some real estate prediction, demand casting, credit risk assessment, or pricing model. So it's like if I have some kind of subset of discrete information, but tomorrow someone wants to ask me about one input information that I don't have, I need to go to kind of functional regression model. Is it clear? Question? No? Sure? Perfect. And when we are not talking about supervised, we are talking about unsupervised learning. Here we didn't have this label. Because when we are training here, we have some label is, yes, I'm training my algorithm to see that if it's cat or it's dog. So I show the cat, I show the dog. And after, when it learns that black box learn, it will say that when the error is less or zero, close to zero, this algorithm can say that, yes, I can classify what we are talking about. In this case, we don't have it. We don't have this. Okay? Is the reason of that is unsupervised. You don't have it. But this algorithm is used to make some kind of classification, clustering. So I have a amount of data, I have a amount of things, and I need to classify those things. Not classify, to make clusters. And I need to make some kind of cluster of the input data. So we use these techniques to make this kind of cluster. Or I have a lot of data, and I want to change the dimension of the data. I want to reduce the volume of data and work with some kind of representative set, but I don't know how to do it. The way to transform this is like something that they call PCA. With the PCA, I can change the dimension of the data and reduce the data, the information of data, and with that, I can make all this segmentation, social media analysis, and so on. Okay? And between these two, we have the reinforcement learning. And this is used a lot in the Boston Dynamic, the dog, and behavioral stuff when we want to analyze the behavior of a human being, and also the data, what we use is the reinforcement learning. And it's very, very interesting. The difference between these is that you don't have this information, but you have some kind of reward. So you give a reward to the agent and see that what they are doing is what you expect or not. Okay? And they use this to make all this route optimization. All the car that we see in California, they are using the reinforcement learning algorithm to solve and to make the route and the scheduling optimization. Okay? Trading and robots, all the robots from Boston Dynamic, they are using this kind of algorithm. So, but this is only machine learning, is the part of machine learning. Here we didn't have deep learning. Here we didn't have generative AI. But we know all the most problem that we are trying to solve in our department and entity related to these three words. Okay? Question? With this, we finish the introduction and for AI and so on. So, question? Yes?
I was wondering, you did mention about generative AI. I was wondering, how does it function in relation to all these types? Like say, stable diffusion, how would you categorize that in terms of how it functions?
Yes, it's some kind of generative AI. The architecture is totally different from this. Okay, it's very close to deep learning. Is like the combination of a lot of architecture, and is not too simplest to make some kind of let us say that some kind of introduction. But it's like the combination of because you have a huge data that you need to train the model. And after that, you also need some kind of neural network, like a deep learning, to make all this optimization part and see that what you have makes sense or not. And after that, you have some kind of vectors stuff that you are working with vectorization. So we can talk about that, but for the class, I leave it to make sure that we have the whole focus. Okay, if you have some kind of question, we can solve it after. Okay. Question? No. Clear? Everything is clear? Amazing. I can go forward. Perfect. So. The second part of my presentation is about the humanized ABM, okay, and how we can integrate in Cityscope. But the first thing is about the cities, because city science, we are working with cities. And cities, for us, is the host of social ecosystems. So the social part are very, very important for us. And when we are talking about social part, we have three dimensions. We have the human iteration, that is very important. Okay, we have the economical flow, because the city is the nerve of everything that we know. Without city, we don't have, maybe we will not be here. So it's very important, is where human have iteration and where we can make some kind of transition. And also we have a context of the environment. So these three dimensions combined give us city. But at the end of the day, what we want to see is that, wow, city are very complex system to simulate, to solve. Very complex. It's not easy to solve a city. It's a very, very complex system to solve. Okay. The way that we know to solve complex systems is by using what we call h-ABM, agents-based model. Okay, agents-based model is a kind of let us say the concept, where we have the agent have the rule, that is a rule base, have the environment, have the iteration, okay? But all these are related by a probabilities. So it's not information that we have like natively, it's not information that we have like a human being, it's information that is based on rules. You have to do this, 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 this. You have to do that, 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 that. To move from point A to point B, you need to do this related to the rule that I'm writing, I'm giving you. Okay? So, if we use ABM to simulate a complex system like a city, and the rule that I'm defining are very, let us say that, has bias, are not very representative of what I'm trying to solve. Maybe I have a headache. Maybe this will not give me all the qualitative information that I need to make the simulation that we want. Maybe here something that we have a rule is that you will be in this class, but in 5 minutes, maybe you decide to leave the class. But if this is not in your role because you are not feeling well, not in your role, this is some kind of information or some kind of situation that we will not say. Okay? So if we want to use the ABM model to simulate the very complex city, we can find some kind of limitation. So what we said, rule-based sometimes can be simplistic to provide useful information for human decision making. Not always, but there's a lot of a scenario that this has a lot of constraints. Training native and rule-based can expose community to privacy breaches. This is, yes, we need a lot of data and we need people data, people information to make these rules. Okay? So advanced calibration of ABM aligned with human behavior are very difficult to do. So we cannot write down all the rules how like a human behave to do that. Okay? But we are city science and we want to analyze the city of the future. We want to create some kind of living lab where we can put these agents or those agents inside this laboratory, simulate, explore all the possibility before deciding which kind of city that we want or not. And maybe these agents need to make some kind of decision, need to vote, need to tell us if their behavior or they are feeling well or not in this place or another place. So this could be very, very, very difficult. So our focus is use native AI systems, all the AI systems that we have seen, machine learning, deep learning, neuronal or generative, use this plus LLM plus ABM. If we can make this combination, we can promote enhanced quality of life, because it's one of the main topic from city science. See? Sustainability. If these agents has this ability, or like a human feature, and they can tell us that they don't like it, they like it, this city is hurt, is not hurt, we can have this information and also generate a vibrant and dynamic human fabric. This is what we are following. So, how can we do it? Here we have some kind of simulation where we generate all these agents that here's a Kendall close to MIT, and we have like a Cityscope agent here, and we can chat with this agent and we can ask them how they feel, which kind of amenities they want, where they are going to go, they want to go, which kind of accessibility that they have, which kind of facility that they have or not. We can use this platform that we are building to address these limitation. And also we can vote and see how those agents they agree about having this amenity here or not. If they are not, what they can do or not, having the opinion of this agent, we can do it. So, but by building all these things that you have seen, we have the limitation that we see, the challenge of AI that we have seen before. So how can we humanize the agent-based model? This could be the first question that we have. If we say that the ABM, the native ABM have this limitation, the question is, how can we humanize this? So for us, humanize is not everything, is realistic choice, close to human being. They can learn. This is important. Social connection, that means they can talk, they can chat, they can discuss. The workshop that we prepare today, at the end of the class, we show that part of this social connection and discussing very, very good topic, okay? And diversity. So for us in city science, we are saying that humanized ABM is giving this ABM this 4 dimension, okay? By having this 4 dimension, we can work to extract this qualitative information that we need to design the city of the future. There's a lot of people that they are thinking about a structural or unstructural data, and they are saying how to map them. But in our case, it's important, but as we have to project the city of the future in 5 or 10 or 20 years, we need kind of information, but also we need some kind of, let us say that free will to see that what we are having makes sense or not makes sense. And this is important also, because if we want to create something based on what we have, only what we have today, maybe it will not work in the close future. Maybe we need some kind of free will to see if this is hallucination or not. So this is important for us. Okay. So, and in the reason of that, we defining what we call humanize, because humanize, we can do a lot of things, but we want to make sure that the choice is realistic. This is very, very important. And Kai and everyone in the group have projects like choice making, and it is important. Learning, we need our agents learn. If they have some kind of situation, we want to see how this, if they face the same problem in the future, or problem that is related, how they can solve this problem is very important also. The social connection, because we are in city science, and we see that city is the nerve of everything that we are talking about, and the diversity is very important. So yes, it's a little bit in that sense, but now we are going down. For us, how we humanize this is, yes, when we design this is like a year and a half ago. But this last week, I saw that OpenAI also already have the audio contest. So with the mobile phone, you can talk directly to the agent, and the agent behave and answer you. So it's very good. So we are trying to target this 3-dimension demographic information is where we were working census data and so on, that and pictures. The picture we didn't do it is one of the questions, and I think that people in the group are doing. Here is like we make some kind of sum, and with LLM and neural network, this native AI, what we are trying to do is making some kind of semantic search and working in some kind of induction reasoning search is what we were thinking, because for us, the brain, what we are using from the LLM is like the part of induction. It's not the part of answering, the induction part. So this can give us state analysis, opinion, and sentiment. This is some kind of architecture that we are following. And in our case, in city science, how can we integrate all this into city science? So we have some kind of tools that we call Cityscope, and we have also Cityscope GS. We have one ABM platform that is Gamma, that have ABM functionality feature, and using some kind of library that we are building, we can embed all this information into the Gamma that is about the basic ABM mobility, and this to Cityscope, and we can have something like that on the video that I show you. Okay? Why LLM has hallucination? This could be a question for us also. Why?
Well, it's mainly data, right? I mean, if you have bad data, it produce bad outputs.
Bad data. Which data are you talking about? The training data or the information that we are?
Training data, I guess.
Imagine that you have in your basement Albert Einstein. Okay? You know about physics, you know about everything. And you want to ask him about city science. And you didn't know how to formulate a very well question to Albert Einstein. The answer that he will give you will be with hallucination or without hallucination? Hallucination. So it's not only about the training data, it's also about how we ask the question. The thing that the people call prompt. This also is very important on that. You can have a most powerful people, but if you don't know how to retrieve the information from these people, you can have hallucination. We have it. We don't need h-ABM. If you ask me about something I didn't understand that I answer, it's some kind of hallucination, okay? So the bias on accurate training data is possible, is important, is what we are saying, but it's not only that. If we focus only on that, we will miss how to take an advantage of the tool that we have. Lack of true understanding, this is important. Context limitation is what we were saying, and overgeneralization, okay? And how we reduce it, we use memories, is important, memories, okay? Some kind of strategy. And into this strategy, we have these vector database techniques that we can talk deeply. And at the end of that, we have some kind of proposed architecture that help us to separate all this information.